Antarctica is not just a vast icy desert, but a whole continent hidden under kilometers of ice, containing mountains, valleys, and lakes hidden from human eyes. This frozen world is comparable in size to Australia, and its grandeur is hard to overestimate. The heights of the mountain ranges in Antarctica reach 3,000 meters, while deep valleys and plains create a unique landscape that, if visible without the ice cover, would be striking in its contrasts. Imagine dark rocks sharply rising from light plains, as if frozen in anticipation, interrupted by winding riverbeds where once crystal-clear waters flowed. These rivers and lakes, such as Lake Vostok, located under 4 kilometers of ice, have their own unique ecosystems that can exist in complete isolation for millions of years. Research conducted by Russian scientists in 2011 showed that Lake Vostok is home to numerous microorganisms that have survived since prehistoric times. The ice of Antarctica hides not only natural beauties, but also unique climate records that can shed light on the history of our planet. Over the past 18 million years, multiple temperature fluctuations have left their mark on the layered ice deposits, and each layer tells a story of climate changes that occurred on Earth. These data are important for understanding current climate changes, as they help scientists predict how our planet will look in the future. Complex geological processes, such as plate tectonics, have shaped this continent, which continues to be one of the least known and most inaccessible places on Earth. In 2020, international research groups using modern technologies such as satellite imagery and radar methods discovered under-ice lakes and mountain ranges that were previously unknown. This information changes our understanding of the geography of Antarctica and raises questions about how these hidden landscapes can affect global ecosystems and sea levels. Antarctica is not just a cold continent, it is a unique ecosystem full of mysteries and riddles waiting to be discovered. For example, a study conducted in 2018 showed that under the ice cover, there are not only bodies of water, but also significant carbon reserves that can influence global climate. The height of the ice shield in some places reaches 5 kilometers, creating pressure that affects tectonic processes beneath it. On the continent, unusual meteorological phenomena, such as Antarctic cyclones, which can reach hurricane strength, have been recorded. It is important to note that the Antarctic coastline and its glaciers continue to actively respond to climate change, and according to research, the rate of ice melt has increased threefold over the past 30 years. This process not only changes the landscape, but also threatens ecosystems that depend on the stability of the ice cover. As can be seen, Antarctica is not just an icy abyss, but a complex system that requires further study and understanding. Scientific expeditions, such as those conducted by polar stations, continue to uncover new facts about life in this harsh climate. Beneath the thick ice of Antarctica lies a hidden world of water, unknown to many. 80,000 years ago, when the climate was vastly different, life thrived on the surface of Antarctica, now concealed under the ice cap. One of the most famous subglacial lakes is Lake Vostok, which is comparable in size to Lake Ontario and has a maximum depth exceeding 900 meters. The discovery of this lake became possible thanks to radar studies conducted in the early 1990s by a team of Russian scientists led by academician Valery Lunin. The studies revealed that beneath the ice cover lies not just a body of water, but an entire ecosystem isolated from the outside world for millions of years. The process of discovering these lakes was a true scientific breakthrough. Using radar systems, scientists were able to detect the presence of liquid water under the ice, which is in itself an extraordinary fact. It is interesting to note that the temperature of the water in Lake Vostok remains positive due to geothermal heat from the Earth and the pressure of the overlying ice, preventing it from freezing. These conditions create a unique habitat where microorganisms adapted to extreme conditions can exist. Research on Lake Vostok continues, and scientists hope to find unique forms of life there that could provide insights into how life might have evolved on other planets, such as Europa, a moon of Jupiter, which also has subglacial oceans. Exploring such ancient water bodies is not only a scientific discovery, but also a step into the unknown, opening new horizons of understanding life on Earth. Scientific expeditions using specialized equipment allow for the extraction of water samples and sediment samples, enabling researchers to study the chemical composition and search for signs of life that may have existed in these isolated water worlds. Scientific data indicate that subglacial lakes like Lake Vostok may contain biological traces that will help in understanding the evolution of life in conditions similar to those on other planets. Each new fact about such lakes as Lake Vostok underscores how little we know about our own world and how many surprises it still has in store for us. Antarctica is not just a continent of ice and snow, but a true giant that holds approximately 70% of all fresh water on the planet in the form of frozen ice. If all this ice were to melt, the level of the world ocean would rise by impressive 58 to 60 meters, which would be equivalent to the flooding of the largest coastal cities in the world. Imagine the water rising, flooding the streets of New York, London, and Tokyo, and how all this fresh water, trapped in ancient ice, could change the face of our planet. The ice in Antarctica has unique properties. It contains crystal-clear water that is so transparent that one can see to a depth of dozens of meters. This purity has no equivalent on Earth, and each piece of ice you observe is the result of a 1,000-year process of snow compression and freezing, gradually transforming into massive ice sheets. When sunlight hits the ice, it is refracted, creating unique shades of blue and turquoise that captivate with their beauty. This effect is achieved because the ice scatters light, and the deeper it is, the more saturated its shades become. Gazing at these enormous ice formations, it is hard not to ponder how many stories and climatic changes they could tell if they could only speak. Glaciers like the Taylor Glacier reach heights of over 1,800 meters and extend for tens of kilometers, creating true ice rivers. In this harsh environment, scientists find microscopic organisms that survive in extreme temperatures, and studying their genetics may provide keys to understanding life on other planets. Studying Antarctica not only opens new horizons in science, but also makes us realize how vulnerable our planet is. Each ice layer we study can tell us about climatic changes that occurred on Earth over millions of years, and how these changes affected flora and fauna. Scientific projects, such as the MIT program for studying Antarctic ice, continue to reveal new facts about the composition of the atmosphere and climatic changes that occurred in the past. Antarctica is not just a cold, desolate continent. It is a repository of ancient history waiting to be discovered. Imagine a future where the melting of Antarctic ice leads to a new reality, where coastal cities disappear under waves. Over the next 100 years, the global sea level could rise by 1 meter, meaning that the Netherlands, already below sea level, will be submerged. In Bangladesh, with a population density of over 1,000 people per square kilometer, millions will be displaced, losing their homes and livelihoods. Venice, famous for its romantic canals, will become a part of history as its waters rise, flooding squares that were once full of life and tourists. St. Petersburg, founded by Peter the Great, will also be at risk, as its unique architecture and cultural heritage will be swallowed by the sea. New Orleans, already suffering from hurricanes and floods, will become another victim of ocean waves. The sound of retreating water will be heard for many kilometers as it slowly but inevitably takes over the land, leaving behind destroyed homes and flooded streets. The salty smell of the ocean will penetrate deeper into the continent, altering the familiar landscape and ecosystems. New shorelines will form where houses once stood, and instead of familiar streets, there will be murky waters. These changes will not happen instantaneously, but over centuries, creating a continuous process that will be irreversible. An increase in sea level by 2 meters by the year 2200 could lead to global population migrations and changes in ecosystems that we cannot even imagine. In some regions, such as the Maldives, losses could exceed 90% of the territory. These events will have significant economic and social consequences, as more than half of the world's population living in coastal areas will be at risk. Climate change is already affecting our future, and it is time to prepare for it. The Antarctic ice represents not only a massive body of frozen water, but also a unique archive that preserves the atmosphere of past eras. Within this ice are tiny air bubbles that serve as true time capsules. These bubbles have captured the composition of the atmosphere when snow was just beginning to settle on the continent's surface. Over thousands of years, layer by layer, each new snow compacts under the pressure of the previous layers, first turning into firn and then into dense ice. This process begins when snow crystals, falling to the ground, gradually lose their lightness and start to compress. As a result, after tens and hundreds of thousands of years, ice masses form, containing air bubbles that date back thousands of years. For example, samples taken from the depths of ice in the region of eastern Antarctica have revealed bubbles dating back to the last ice age, which began approximately 180,000 years ago. These bubbles allow scientists to analyze the composition of the atmosphere by studying the levels of carbon dioxide, methane, and other greenhouse gases, providing insights into climate changes. Additionally, the Antarctic ice contains particles of dust, volcanic ash, and other materials that could have entered the atmosphere due to natural processes. For instance, samples collected during an international expedition in 2012 contained traces of volcanic activity dating back to the eruption of Krakatoa in the 1880s. These samples enable scientists to track how the atmosphere and climate have changed over centuries and to identify patterns that may help in predicting future climate changes. Ice cores extracted from the depths of Antarctica can reach lengths of up to 100 meters and contain layers that form an almost ideal timeline for studying climate changes. Within these layers, there are not only air bubbles, but also tiny particles that can provide information about how the composition of the atmosphere has changed due to natural and anthropogenic factors. Antarctica, as we know it today, is the result of a long and complex process that began around 34 million years ago, when the continent separated from Gondwana and began to move towards the South Pole. When Antarctica started this journey, the climate was significantly warmer than it is now, and its surface was covered with lush forests teeming with diverse flora and fauna. Fossil remains indicate that at that time, Antarctica was home to coniferous trees such as Araucarias and Podocarpus, as well as many other plants characteristic of warmer latitudes. However, as the continent gradually moved towards the pole, temperature conditions began to change. Around 30 million years ago, the climate started to cool, and the continent underwent transformations that eventually led to the formation of an ice sheet. Soon after, over millions of years, the landscape began to change. The rich forests gave way to tundra, and then to an ice desert. The appearance of the first glaciers was noticeable not only in the mountains, where they began to form, but also in the valleys, where they slowly descended, covering new territories. These glaciers grew, turning into powerful ice shields that in turn began to shape the region's relief. One of the most significant events of this period was the formation of the East Antarctic ice sheet, which now covers more than 90% of the continent's surface. The ice sheet reached thicknesses of up to 4 kilometers in some places, and its mass affects the level of the world's oceans. This process was relentless and slow, and although changes took place over millions of years, they had a profound impact on Earth's climate and the biological diversity of the region. As a result, by the end of the Miocene, around 17 million years ago, Antarctica looked completely different from when it separated from Gondwana. It had become an ice desert, where harsh conditions reign, unfamiliar to those who have ever seen its forests. The ice shield of Antarctica is a complex system divided into eastern and western shields, each with its own characteristics and dynamics. The eastern shield, covering approximately 4 million square kilometers, is twice as large as its western counterpart and has an average thickness exceeding 3,000 meters. The western shield, while smaller in area, is characterized by significantly thinner ice and faster glacier flows. Ice moves slowly from the continent's center to the ocean at a rate of several centimeters to several meters per year, creating the impression of a slow but inexorable process. These glacier flows and ice shelves, such as the Larsen and Thwaites glaciers, are important components of the ecosystem where ice meets the sea, forming majestic icebergs. The sounds accompanying the movement of ice resemble the cracking and creaking that can be heard from a distance when vast masses of ice shift, creating muffled rumbles, as if nature itself is playing music. From a bird's-eye view, these flows appear as slow rivers carving through the snow-white plateau, covering its surface. Research conducted by scientists from NASA and other international organizations shows that glaciers, such as the Pine Island Glacier, lose around 130 billion tons of ice annually, affecting the global ocean level. Comparing glacier flows to rivers is not coincidental. They lead their own lives, slowly but steadily depleting ice reserves, and their dynamics are influenced by air and water temperature changes, as well as climate shifts. Each crack and flow reflects the history of climate change, and scientists like Professor David Weiss Stevenson have been documenting these changes over decades, tracking how the ice shield responds to global warming. In the 21st century, the consequences of temperature changes have become apparent, with some regions of Antarctica experiencing accelerated ice melt at rates never seen before. This has led scientists to continue sounding the alarm, emphasizing that the rate at which ice is lost could significantly impact future ocean levels and climate conditions. This is particularly true for ice shelves, which act as barriers slowing down the flow of ice into the sea. Scientists from the University of California assert that with further increases in ocean and air temperature, these barriers could be breached in the coming decades. Such events are not just theoretical, they are real changes that we can observe today. In the 21st century, the ice shield continues to be a subject of intense scrutiny, and data on its changes are becoming increasingly relevant in light of the modern climate changes occurring on our planet. The ice continent of Antarctica is not just a vast mass of ice, but a crucial element of the global climate system. The cold air that forms over its surface creates powerful circulation currents in the atmosphere, which in turn influence weather conditions worldwide. Specifically, these currents contribute to the formation of anticyclones and cyclones that traverse the planet. Consequently, changes in temperature in Antarctica can trigger a chain reaction affecting climate conditions on all continents. The oceans surrounding Antarctica, such as the Southern Ocean, serve as the site for the formation of cold bottom waters, which play a critically important role in the global ocean conveyor. These bottom waters, rich in oxygen, move through the ocean, interacting with warm currents and creating complex water movement systems. Notably, Antarctica is the source of what is known as the deep current, which begins along the coast and spreads throughout the world ocean, maintaining the necessary balance of temperatures and salinity. Research conducted by scientists at the Scripps Institution of Oceanography in 2018 demonstrated that this current facilitates the redistribution of heat, impacting climate conditions in remote regions such as the tropics and even the Arctic. For instance, if temperatures in Antarctica begin to rise, this could alter the direction of ocean currents, leading to changes in the distribution of precipitation, sea levels, and even ecosystems. An increase in temperature on the ice continent could also accelerate the melting of ice, resulting in the discharge of fresh water into the ocean and altering salinity, which is critically important for marine life. As a result, changes in Antarctica reverberate like an echo in the most distant corners of the Earth, impacting the lives of millions of people, animals, and plants. In 2020, scientists determined that the melting of the ice cover in Antarctica could lead to a rise in sea levels of up to 2 meters by the end of the 21st century, affecting coastal cities and ecosystems worldwide. These findings underscore the scale and significance of Antarctica as a key player in the global climate system. In Antarctica, the process of converting snowflakes into ice is a remarkable phenomenon that spans decades and even centuries. Snowflakes settling on the surface begin to lose their original lace-like structure. Each new layer of snow that falls above exerts pressure on the layers below, causing them to compact. At this stage, snow starts to transform into firn, a granular, semi-transparent material that retains some characteristics of its predecessor but differs significantly in density. During compaction, the density of snow increases from about 80 kilograms per cubic meter to 130 kilograms per cubic meter, and its color changes from bright white to a slight grayish hue. Gradually, under the influence of pressure and temperature, firn begins to transform into crystalline ice. This process can take from tens to hundreds of years, depending on the climatic conditions and the thickness of the snow cover. When light hits the ice, the crystals refracted, giving it a characteristic bluish tint. Thus, when we look at the ice caps of Antarctica, we are not just seeing frozen water, but a multi-layered history of climatic changes accumulated over millennia. Each layer of ice preserves information about the past, from atmospheric conditions to volcanic activity, recording changes in the composition of the atmosphere and temperature. On July 18, 2003, during research conducted by the International Program for Ice Core Studies, it was discovered that in a sample over 800,000 years old, traces of ancient gases were found, allowing scientists to glimpse the climatic conditions of past eras. Such ice is not just a material, but an archive of time, enabling us to understand how the planet has changed and what threats are looming due to global warming. With every meter we traverse, studying glaciers, we uncover new pages in the book of Earth's history. The ice masses that cover Antarctica and Greenland possess such a complex structure that their formation is a true physical spectacle unfolding over thousands of years. Under the weight of multi-kilometer layers of ice reaching heights of 3 to 4 kilometers, pressure on the lower layers becomes immense, exceeding hundreds of atmospheres. This pressure forces air out of the crystalline lattice of the ice, altering its structure and density. Thus, at depths of several hundred meters, ice can reach a density of up to 900 kilograms per cubic meter, and with further immersion, it becomes even denser, sometimes forming ice with unique crystalline structures that are invisible to the naked eye. For instance, in certain parts of the Greenland ice sheet, ice crystals in the form of monocrystals have been discovered, indicating how physical conditions change at different depths. At levels where pressure is particularly high, temperature can rise to 0 degrees Celsius, sometimes even becoming positive due to geothermal heat emanating from the Earth's crust. This creates conditions where ice begins to melt and form subglacial waterways, which in turn influence the movement of glaciers and their stability. These invisible processes occurring within the ice sheet can cause significant changes in the glacial landscape that remain unnoticed until they become visible on the surface. For example, in 2012, scientists observed that in some areas of Antarctica, the rate of ice melt had increased by 30% compared to previous decades. This underscores how physical changes deep beneath the ice can impact global climate processes. By studying ice cores, we not only obtain samples, but also gain insights into the climatic history of our planet. Imagine a world beneath the icy cover of Antarctica, where ancient landscapes have been preserved in a state of freeze for millions of years. These landscapes, comprised of mountains, valleys, and lakes, can provide insights into what this part of the world looked like before the onset of glaciation. For instance, geologists have found that some of these landforms have remained unchanged since the glaciation began around 30 million years ago. This means that under the ice sheet, one can find almost untouched ecosystems that thrived during a time when the climate was significantly warmer. Research conducted in 2009 revealed that beneath the ice, there are valleys where rivers once flowed and lakes that could have existed in conditions reminiscent of modern-day tropics. A scientific team, led by Dr. Matthew Carey from the University of Adelaide, discovered that under the ice, there are traces of vegetation indicating a more diverse flora than we can currently imagine. The landscapes beneath the ice have retained their shapes and features, allowing scientists to draw conclusions about the geological past of the region. For example, studies of ice cores have shown that the level of carbon dioxide in the atmosphere was significantly higher than it is now, which could have contributed to a warmer climate. The ice also conservatively preserves microorganisms that can provide valuable information about the biodiversity of ancient ecosystems. By studying these hidden worlds, scientists can reconstruct the climatic conditions that existed in Antarctica before glaciation, which can help us understand how ecosystems responded to climate change in the past. In 2017, a team of researchers from New Zealand used radar technologies to map the subglacial forms of the landscape, revealing that the ice cover conceals not only mountain ranges, but also deep canyons that could have been home to ancient animals and plants. These discoveries open new horizons for understanding the geological history of Earth and its changes. As we delve into the history of Antarctica, it's worth remembering that several tens of millions of years ago, this continent looked entirely different. During the Cretaceous period, around 100 million years ago, Antarctica was part of the supercontinent Gondwana, which united present-day South America, Africa, India, and Australia. Instead of the icy wastelands we see today, there stretched lush forests with giant conifers and abundant vegetation. These forests were home to tropical rains, creating ideal conditions for a diverse array of animals. For instance, dinosaurs, both large herbivores and predators, roamed the continent, leaving deep tracks in the moist soil. At that time, the climate was significantly warmer than it is now, with temperatures sometimes reaching 20 degrees Celsius. Paleontological excavations in the 20th century confirmed the presence of fossils of such animals as Mesozoic reptiles and ancient mammals, indicating a rich and diverse ecosystem. However, due to the movement of tectonic plates, continents began to shift. Gradually, Antarctica separated from the other parts of Gondwana and started drifting towards the South Pole. This process took millions of years, and with each passing million years, the climate on the continent became increasingly cold and harsh. Changes in ocean currents also contributed to the formation of cold currents, further accelerating the glaciation. By the end of the Miocene period, around 10 million years ago, Antarctica acquired its modern ice caps, which now reach a thickness of more than 3 kilometers. These ice sheets hold information about climate changes on Earth, making them a valuable subject of research. Have you ever wondered what life in Antarctica was like when it was covered in green forests instead of icy deserts? Research conducted in the Transantarctic Mountains has revealed fossils of plants and animals that indicate this continent once supported a diverse ecosystem. For instance, fossils of Glossopteris, an ancient fern with sickle-shaped leaves up to 30 centimeters long, have been found in rock layers dating back around 250 million years. These plants created dense forests that were home to various animal species. The discovery of dinosaur remains, such as maniraptors, which lived in this warm climate, is equally impressive. These reptiles could reach lengths of up to 2.5 meters and may have emitted sounds similar to modern birds, filling the air with melodic trills and cries. Scientists studying these findings suggest that the climate in those distant times was significantly warmer, with average temperatures possibly reaching 20 degrees Celsius. The air was filled with the scent of blooming plants, and the forests teemed with life, from insects to large herbivores like dinosaurs, which left tracks in the soft soil. This ecosystem could have been as diverse as modern tropical rainforests. For example, finds near the Ferordi River indicate that giant conifers, reaching heights of 30 meters, once grew there. These trees likely provided homes for many animal species that fed on their seeds and fruits. It is important to remember that the climate conditions in Antarctica have changed over millions of years, leaving their mark on the landscape. The formation of the glaciers we see today began around 30 million years ago when temperatures dropped sharply, leading to the extinction of many species. There is evidence that the oceans around Antarctica also changed, causing the migration of many species. Therefore, the study of these fossils not only helps us understand what life was like in the past, but also shows how quickly the climate on our planet changes, leaving traces that will be studied for many years to come. In the Transantarctic Mountains, where these fossils were found, researchers continue to uncover new artifacts that provide more information about the ancient life on this continent. Imagine a continent that was once covered in lush forests and teemed with diverse life, but now has become a silent ice kingdom. The transformation of Antarctica into an ice-covered state began around 34 million years ago, when the climate began to change and the first glaciers started to form on the continent. This process was not instantaneous, but took millions of years, during which the world grew colder and the landscape underwent significant changes. Forests that once covered much of the continent began to retreat, giving way to rocky wastelands and ice sheets. Studies show that the soil gradually froze and the surface temperature dropped significantly, leading to the extinction of many plant and animal species that could not adapt to the new conditions. During this time, animals such as mammals and reptiles began to migrate to warmer regions or became extinct if they couldn't find suitable habitats. Scientists have found fossils that indicate many species could not survive in conditions where temperatures dropped to critical levels, leading to a significant decrease in biodiversity. The complete glaciation of Antarctica occurred around 14 million years ago, when temperatures dropped so much that glaciers covered the entire continent, creating massive ice shields several kilometers thick. These glaciers not only altered the Earth's topography, forming fjords and deep valleys, but also had a profound impact on global climate conditions, including sea levels and atmospheric flows. Research shows that it was during this period that a new epoch began in the planet's history, the epoch when Antarctica became the ice continent we know today. The ice shields have become repositories of ancient information about the climate changes that have occurred on Earth over millions of years. Plate tectonics played a pivotal role in shaping the climate of Antarctica, and this process was no less significant than the impact of glaciers. Approximately 100 million years ago, during the Cretaceous period, Antarctica separated from Australia and South America, which served as a catalyst for the formation of the circumpolar current. This current encircled the continent, creating a powerful cold barrier that isolated it from the warm waters of the equator. The circumpolar current, one of the strongest oceanic currents, began to form at the time when tectonic plates started moving. leading to significant changes in oceanic circulation. As a result of Antarctica's isolation, the air temperature on the continent began to drop, and the Antarctic ice sheets began to develop, reaching their current scales. The process of forming this current took millions of years, and its influence became evident not only for Antarctica, but for the global climate as well. The impact of the circumpolar current is seen in the changes of temperature regimes not only in the southern hemisphere, but also across the entire planet, as it influences the climatic conditions in other regions such as South America and Australia. Since the formation of the circumpolar current around 40 million years ago, a new epoch in Earth's climatic history began, during which the continent became almost entirely covered in ice. This was made possible by the cold waters circulating around Antarctica, preventing warm waters from reaching its shores. Despite global warming in other regions, Antarctica maintained its icy cover, which according to scientists' estimates may contain around 70% of the planet's fresh water. These changes in oceanic circulation served as the foundation for numerous climatic effects, including the intensification of cyclones and changes in weather patterns in the southern hemisphere. The formation of the powerful ice sheet on Antarctica and its influence on global climatic systems remain relevant topics in climate research. In recent decades, scientists have observed how changes in the circumpolar current can affect sea levels, which in turn poses a challenge to coastal regions worldwide. The breathtaking journey into the unknown began in the 18th century, when seafarers, driven by dreams of new horizons, embarked on perilous expeditions. James Cook, the renowned English explorer, crossed the southern polar circle in 1773. His crew, with tense faces and hearts filled with hope, battled icy winds that burned their faces, while the creaking of the ship's rigging created a haunting symphony of the sea. Cook did not see the continent, but his courage and desire for discovery laid the foundation for future expeditions. Just over half a century later, in 1820, Russian explorers Fadej Bellingshausen and Mikhail Lazarev, aboard their ships Vostok and Miri, finally reached the shores of Antarctica. Their voyage marked the culmination of years of effort and dreams about the mysterious continent hidden beneath the darkness of the oceans. The icy wind continued to howl, raising snowstorms and creating an atmosphere of discovery. The sea rose as if trying to hold its secrets, and the gleam of ice on the horizon beckoned the explorers like an oasis in the desert. As the ships approached the shores sealed by ice, the sailors felt not only the cold, but also the thrill of witnessing a historic event. A fire of discovery burned in their hearts as they first saw the vast glaciers looming over them like guardians of ancient mysteries. These icy formations, reflecting the sunlight, created a spectacle that would forever remain in memory. Bellingshausen and Lazarev did not just discover the continent, they opened a new era in the exploration of Earth, allowing humanity to ponder what lies beyond the horizon. Their expedition laid the groundwork for scientific research that continued for centuries. On February 18, 1820, they reached the first point in history on the coast of Antarctica, which became the basis for further discoveries, such as the study of the flora and fauna of this enigmatic continent. The era when researchers ventured into the icy wastelands, knowing that their fate could be in the hands of harsh nature, became an age of heroic Antarctic expeditions. Ernest Shackleton's expedition on the ship Endurance in 1915 was one of the most extraordinary examples of human courage. The ship, trapped in the ice, was forced to endure endless months of waiting, while the crew of 28 men battled temperatures down to -50 degrees Celsius, endless hunger, and blinding snow that obscured everything. Shackleton, with his extraordinary charisma and leadership skills, managed to keep the spirit of his people alive when all seemed hopeless. They traversed the ice fields, overcoming not only physical but also psychological obstacles. Each step in the constant cold and lack of food became a true test, but Shackleton and his team survived. In 1917, they reached South Georgia to summon help and eventually returned for their companions. Meanwhile, Robert Falcon Scott and his rivals, including the Norwegian Roald Amundsen, sought to be the first to reach the South Pole. Scott, who embarked on his expedition in 1910, was driven by the spirit of discovery, but his tragic death in 1911 became a poignant symbol of the fragility of human life in the face of nature. After reaching the pole, they discovered that Amundsen had beaten them by 34 days. Scott and his team, returning, faced unbearable conditions and, lacking sufficient food, perished on the way back, becoming victims of the harsh climate and their own ambitions. Amundsen, on the other hand, demonstrated brilliant planning skills, using dog sleds and adapted tactics, which allowed him and his team to reach the pole in 1911. His approach to preparation and understanding of the Antarctic environment became the foundation for future expeditions. He knew that Antarctica was not just a cold desert, but a place that required respect and understanding. As a result, his team not only achieved their goal, but also returned home alive and unharmed, unlike Scott. These sagas, filled with courage, heroism, and tragedy, highlight how researchers fought not only against nature, but also against themselves. Hunger, cold, and physical exhaustion became constant companions of these brave individuals who risked their lives for knowledge. 87 days of complete isolation with minimal food supplies, life in tents at temperatures reaching -50, and constant pressure to survive, all became part of their lives. Shackleton, Scott, and Amundsen are not just names in history. They are symbols of human resilience in the face of unpredictable nature. All these trials became the basis for understanding the importance of considering climatic conditions and adapting to them. These expeditions laid the foundation for modern Antarctic research and inspired subsequent generations of researchers. The tragedy of Scott and the triumph of Amundsen continue to be at the center of Antarctic research, underscoring that every mistake or underestimation of nature can have fatal consequences. As a result, Antarctic research became not just an exploration of physical space, but also a deep study of human nature. Modern scientific expeditions to Antarctica are a true fusion of harsh conditions and advanced technologies, opening new horizons in the study of this unique continent. Over the past decades, scientists have actively employed ice drills capable of penetrating to depths of up to 3 kilometers to study subglacial lakes, which have been found to harbor life in extreme conditions. For instance, the Subglacial Antarctic Lakes Scientific Access, or SALSA project, initiated the study of Lake Vostok, one of the largest subglacial lakes, located under an ice sheet more than 3 kilometers thick. These drilling rigs resemble massive metal syringes, allowing scientists to obtain water and sediment samples without damaging the ice cover. They produce dull sounds as they pass through the ice, followed by a characteristic whistle when they reach the water. Robots also play a crucial role in these investigations. For example, autonomous underwater vehicles, such as Seabed, are used to visualize subglacial ecosystems, providing scientists with data on the composition and structure of the underwater environment. These devices operate on batteries and can explore depths inaccessible to humans. Their robust bodies can withstand high pressure, and built-in cameras and sensors allow real-time data transmission to research stations. Scientists at stations like McMurdo control these devices using specialized software, monitoring their movements and collected data. This process demands high concentration and precision, as any mistake could result in the loss of expensive equipment. In such conditions, where temperatures drop to -40 degrees and blizzards can disrupt communication, technologies become indispensable assistants. Modern scientific instruments not only help us better understand climate changes occurring in the Arctic and Antarctic, but also track the consequences of global warming. For example, data on ice thickness and water temperature obtained from these advanced devices help model future sea level change scenarios. Research into subglacial lakes like Lake Vostok shows that even in the most extreme conditions, life can exist, belonging to microorganisms adapted to the absence of light and high pressure. This life may provide insights into Earth's evolutionary processes and even suggest the possibility of life on other planets, such as Europa, Jupiter's moon. Subglacial landscapes, hidden beneath a multi-kilometer layer of ice, are more than just frozen emptiness. Modern scientists use radar and seismic studies to explore these inaccessible territories. Radar systems, operating on the principle of transmitting radio waves, penetrate the ice and register reflections from the boundary between the ice and the subglacial surface. In this process, radio waves sent through the ice can reach depths of several kilometers, allowing for data on the structure and thickness of the ice. The resulting radargrams are graphical representations of the subglacial relief profile, where different colors and shapes indicate changes in the density and composition of the subglacial layers. For example, a study conducted in 2017 by by a group of scientists led by Dr. Eric Black showed the presence of a subglacial lake with an area of about 10 square kilometers under the ice of Greenland, using these very radar technologies. On the other hand, seismic methods involve creating artificial sound waves that penetrate the ice and reflect off various layers, allowing for the creation of a three-dimensional image of the hidden landscape. These sound waves can be generated, for instance, by explosions or hammer strikes on special platforms, and are registered using microphones placed on the surface of the ice. Thus, seismic research not only allows for the determination of the thickness of the ice, but also reveals the presence of subglacial bodies of water and other geological structures. As a result of such research conducted in 2019 by a team of scientists from the University of California, a multi-layered subglacial relief was discovered in the region of western Antarctica, which includes both deep depressions and elevations, indicating complex geological processes that have occurred in this region over millions of years. These technologies open up new horizons for understanding climatic changes and geological processes that have occurred under the ice throughout geological history, making them incredibly important for further research. Subglacial landscapes hidden beneath layers of ice play a crucial role in the dynamics of glacier movement and consequently in global climate. The shape of the subglacial topography determines how glaciers move. Valleys act as channels, guiding the flow of ice, while uplands and mountain ranges create obstacles, slowing or even stopping its movement. For instance, a study conducted in 2009 by a group of scientists from the University of Washington State showed that subglacial lakes near glaciers can significantly accelerate their movement. These lakes, formed from meltwater, act as a lubricant, allowing the ice to slide more easily over the subglacial surface. Thus, subglacial lakes, such as Lake West Antarctica, can create conditions for accelerated melting and movement of glaciers. In this context, it is important to note that subglacial rivers, formed from meltwater, can alter the speed and direction of glacier movement, which in turn affects sea level. According to NASA data, in 2020, the rate of glacier retreat in West Antarctica increased by 800 meters per year, suggesting that hidden landscapes have a direct impact on such changes. Understanding these interrelationships becomes critically important for predicting future changes in the ice sheet, as each change in the subglacial ecosystem can lead to significant consequences for the planet's climate. For example, in 2012, scientists from the Alfred Wegener Institute for Polar and Marine Research discovered that subglacial structures can influence the rate of glacier melting by up to 30%. This underscores the need for a comprehensive study of the invisible subglacial world to better understand its influence on visible processes on the surface, such as sea level and climate change. The global picture becomes clearer when we realize that each glacier is not just a mass of ice, but a complex system interacting with numerous factors that we have not yet fully explored. Imagine vast ice streams, like slow-moving rivers, flowing across the surface of Antarctica, leaving behind traces of their powerful motion. These ice masses, sometimes reaching several kilometers in width and up to 3 kilometers in thickness, slowly flow from the continent's center to the coast, driven by gravity and internal pressure. Over millennia, they form glaciers that then become ice shelves, floating on the ocean's surface and connecting land to sea. In particular, the Ross Ice Shelf, covering approximately 91,000 square kilometers, is one of the largest and most studied in the world. It supports a complex ecosystem where fresh and salt water meet, creating unique conditions for marine life. It is important to note that glaciers are not static. They are subject to various physical processes. When icebergs calve, sometimes reaching the size of small countries, it is a breathtaking sight. Massive ice blocks break away from the main masses with a loud crack and roar, creating powerful waves that can travel into the open ocean. This event is accompanied by sounds ranging from quiet cracking to deafening roars as the ice crashes into the sea. You can feel the vibration under your feet when standing on the surface of an active glacier, as if the Earth itself responds to the power of these natural processes. The dynamics of ice movement in Antarctica also depend on temperature and environmental conditions. For instance, due to global warming, glaciers may accelerate their movement, leading to an increase in the volume of icebergs calving from the shelves. For example, in 2017, scientists observed the calving of an iceberg with an area of nearly 5,000 square kilometers from the Larsen C ice shelf, which caused concern among climatologists as it could indicate more serious changes in the ice system. Glaciers moving towards the ocean can reach speeds of several meters per day, and this process not only affects sea levels but also global climate conditions. Studying these phenomena requires not only careful observation but also the use of advanced technologies such as satellite imagery and ground sensors, which help track the dynamics of ice movement and its impact on the environment. Such research, conducted for example by scientists from NASA and other research institutions, provides valuable information about how ice flows interact with the ocean and atmosphere, shaping climate conditions on the planet. In the depths of Antarctica, processes are hidden that, at first glance, contradict the obvious. Forces are at work under the ice mass that can change its shape and location. Geothermal heat from the Earth's interior plays a key role in this interaction. At a depth of several kilometers under the ice shield, temperatures can reach 40 degrees Celsius due to radioactive decay and residual heat from the planet's formation. This heat warms the lower layers of ice, causing them to melt and form a thin layer of water between the ice sheet and the underlying surface. This water acts as a lubricant, significantly facilitating the movement of glaciers, allowing them to slide and move faster than if they were completely frozen to the base. In some regions, such as the coastal zones of western Antarctica, active volcanic activity is observed, where volcanoes, such as the Transantarctic Mountains volcanoes, are hidden under the ice cover. Volcanic activity raises the temperature under the ice and creates hot springs that also contribute to melting. For example, a study conducted in 2017 showed that geothermal zones with temperatures exceeding 80 degrees Celsius are located under the ice cover of the Antarctic Peninsula. The contrast between the icy cold surface and the heat emanating from the Earth's interior is particularly noticeable in places like the Bennett Zone, where hot springs literally carve their way through the ice, creating unique landscapes. This process not only affects the speed of glacier movement, but also contributes to global sea level changes, as melting ice adds to the oceans. Glaciers like the Thwaites Glacier represent a true management system in this context. Their speed and volume have a direct impact on the future of the planet. In particular, the rate of retreat of the Thwaites Glacier has increased significantly in recent years, directly linked to the rise in temperature and the increasing level of geothermal heat. This raises questions about how quickly climate changes can occur and how they can affect coastal regions around the world. Research shows that despite the remoteness of this region, its state can have catastrophic consequences for the population on other continents. Therefore, the ice shields not only preserve ancient history, but are also active participants in modern climate changes. It's hard to imagine, but in the deep waters around Antarctica lies an ecosystem teeming with remarkable creatures that have adapted to extreme conditions. In these cold, dark depths, giant spiders with diameters up to 30 centimeters and long, thin legs that allow them to gracefully move across the seafloor inhabit. These spiders are predators, hunting small invertebrates like marine worms and mollusks. Their bodies are covered in a hard exoskeleton that protects them from predators and strong currents. In the icy waters, one can also encounter the antifreeze fish, which can survive temperatures below 0 degrees Celsius. This fish, known as the Antarctic cod, possesses a special protein that prevents ice crystals from forming in its body, allowing it to swim freely in freezing waters. Some species of this fish can reach lengths of up to 1.5 meters and typically have a smooth, silvery body that helps them blend into their surroundings. In the Antarctic depths, various invertebrates such as starfish, sponges, and shrimp also live. They use their bright colors to attract mates or repel predators. For example, a starfish with bright red rays looks like an underwater flower in the darkness, and its slow movement creates a sense of fluidity and grace. These creatures often crawl along the bottom, using their appendages to move and search for food. In the constant cold, their metabolism slows down, and they can go without food for a long time. Hunting becomes an art in these conditions. Many predators wait for their prey to be within reach before striking quickly. The defensive mechanisms of these organisms are also unique. Some marine worms release toxic substances to repel enemies, while others can change color to blend into the background. This ecosystem, full of life, may seem inhospitable at first glance, but it is here, in the vast expanses of Antarctic waters, that a constant struggle for survival takes place. Often, in the darkness of the depths, bioluminescent organisms can be seen, which emit light, creating a mysterious atmosphere. These organisms use light as a means of communication or attracting prey. Bioluminescence, for example, in some species of jellyfish, allows them to create mesmerizing visual effects, reminiscent of a starry sky on the ocean floor. In this mysterious world, each creature, regardless of its size, plays a crucial role in maintaining the delicate balance of the Antarctic ecosystem. Research shows that such unique adaptations help these organisms survive in conditions that seem absolutely hostile. In the depths of the Antarctic, bioluminescence becomes more than just a spectacular sight. It is a vital tool for survival. Many deep-sea organisms, such as anglerfish and jellyfish, possess specialized organs that enable them to produce light. For instance, fish from the Opisthoproctidae family, known as lanternfish, have unique light-emitting organs on their heads that emit a blue glow. This light plays a crucial role in their behavior. It attracts prey, particularly small shrimp, which are drawn to the bright light. Light also serves to deter predators. Many deep-sea creatures can momentarily blind their enemies by suddenly flashing light, allowing them to escape into the darkness. Furthermore, bioluminescence is used for finding a mate. For example, male individuals of some deep-sea fish species use light signals to attract females in complete darkness, creating a sort of light show for potential partners. In Antarctica, one can encounter other remarkable creatures adapted to extreme conditions. The transparent bodies of some jellyfish and shrimp allow them to blend into their surroundings, making them nearly invisible to predators. These organisms can survive temperatures close to zero due to the presence of special antifreeze proteins that prevent their cells from freezing. For example, the Antarctic icefish, which inhabits Antarctic waters, can withstand temperatures as low as -2 degrees Celsius, making it unique among its kin. This array of adaptations, from bioluminescence to transparency, allows the inhabitants of the Antarctic depths not only to survive, but also to thrive in the harsh conditions where life seems impossible. Bioluminescence, in general, comes in various shades, from bright green to red, and each creature uses this light in its own way, creating a unique ecosystem where each glow serves a specific function and purpose. In Antarctica, where icy winds reign and temperatures drop to -20 degrees Celsius, even in these harsh conditions, life exists, about which we know too little. Microbial organisms living in dry valleys, such as McMurdo Valley, exhibit remarkable survival abilities. They can remain in a state of dormancy for decades, waiting for more favorable conditions. One such organism is the bacterium Psychrobacter, which can survive temperatures as low as -30 degrees Celsius, using minimal energy to sustain life functions. These bacteria find energy sources in organic remnants, which can be extremely scarce. Interestingly, in saline lakes like Lake Vostok, located beneath a thick layer of ice, microorganisms adapted to high salt concentrations and low temperatures thrive. For example, archaea that can use methane as an energy source play a significant role in the ecosystems of these lakes. Their ability to metabolize under extreme conditions is of interest to scientists, as these organisms could serve as models in the search for life on other planets, such as Mars, where similar conditions may exist. Additionally, bacteria found inside porous rocks can survive without light, using chemosynthesis to obtain energy. These microorganisms can exist in conditions where other forms of life have no chance of survival. They open a window into a world where life adapts and thrives despite seemingly impossible conditions. Studying these organisms provides valuable insights into how life can exist in extreme conditions and aids scientists in the search for extraterrestrial life. In 2023, a group of researchers from the University of California, Berkeley, conducted an expedition to Antarctica to study microorganisms in ice and search for potential signs of ancient life. During these studies, live bacteria were found preserved in ice cores extracted from depths of up to 3 kilometers. This discovery once again confirmed that life in the most extreme conditions not only exists, but is also diverse. Imagine lakes that have not seen sunlight for millions of years, hidden beneath thick layers of ice and protected from the outside world. Subglacial lakes like Vostok, Wilkes, and Ellsworth represent unique ecosystems isolated from the entire biosphere on our planet. Lake Vostok, located more than 3 kilometers deep under Antarctic ice, is one of the largest subglacial lakes in the world, with an area of approximately 11,000 square kilometers. The water in this lake, isolated for millions of years, retains its properties and chemical composition differing from ordinary water. Studies show that the temperature of the water in Lake Vostok remains around -34 degrees Celsius, creating conditions for the existence of unique microorganisms capable of surviving such extreme conditions. In 2011, scientists from the Russian Antarctic expedition successfully drilled and extracted water samples from Lake Vostok. They used specialized equipment to minimize the risk of contaminating the pure water. The samples showed the presence of life forms previously unknown to science, which have evolved independently of the rest of the world. These waters, in addition to simple organisms, also contained more complex forms of life, such as bacteria and archaea, adapted to low temperatures and high pressures. Lake Wilkes, located in western Antarctica, was also the subject of research. In 2015, a team of scientists from the University of Tasmania conducted drilling and extracted samples that showed the presence of unusual methane-producing bacteria, which could provide insights into ecosystems that existed millions of years ago. Another subglacial lake, Lake Ellsworth, can boast of its unique chemical composition, which includes a high concentration of hydrogen sulfide, which may affect the types of organisms living there. These subglacial bodies of water, hidden under thick layers of ice, are true time capsules that have preserved ancient ecosystems that could have existed when the climate on Earth was completely different. It is in such conditions that scientists hope to find organisms that have evolved in complete isolation, which could be a significant step in understanding the origin of life on Earth and the possible existence of life on other planets. The study of these lakes continues, and each new sample may bring discoveries that will change our understanding of biology and ecology. Under ice lakes in Antarctica present scientists with a unique opportunity to study ecosystems that may provide insights into life on other planets. These lakes, located beneath a thick layer of ice, create conditions similar to those that might exist on Jupiter's moons, such as Europa and Ganymede, as well as Saturn's moon Enceladus, where liquid water is believed to exist under an icy crust. For instance, in the 21st century, scientists discovered the Vostok subglacial lake, located over 3,000 meters beneath the ice, with a temperature of around -35 degrees Celsius. This lake has been isolated from the external environment for millions of years, making it an ideal time capsule for studying microbial life. Research conducted here shows that even in the extreme conditions of subglacial lakes, unique organisms can survive in environments that seem completely inhospitable to life. Scientists like Dr. Andrei Polyshuk from the Russian Geographical Society are developing special technologies for drilling and sampling water from these lakes, which can then be adapted for research on other planets. For example, the drilling rig designed to study the Vostok Lake uses a method that avoids contaminating samples, which is crucial for preserving the ecosystem's purity. These technologies will be useful in studying moons where ice crusts may cover oceans, as is hypothesized for Europa, where vast water reserves are hidden beneath the ice. If life can exist in such isolated and harsh conditions as those found in Antarctic subglacial lakes, then it may also exist on other celestial bodies, such as Europa, where eutectic ice layers could provide a suitable environment for microbial life. Such research not only helps us understand how life can adapt to extreme conditions, but also prepares us for future missions to explore other planets and moons. In the 21st century, missions such as Europa Clipper, which will investigate potential oceans beneath Europa's icy crust, are already planned. These studies underscore the importance of Antarctica as a laboratory for studying conditions where life might originate and open new horizons in astrobiology. It is worth noting that as early as 2009, scientists found bacteria in samples from the Vostok Lake, which served as evidence of life in isolated ecosystems. Antarctic ice cores are true archives of ancient climates, preserving information about temperature, atmospheric composition, volcanic activity, and other aspects of Earth's climate history. These cylindrical ice samples, with diameters of about 10 centimeters and lengths of several kilometers, are extracted from deep ice caps using specialized drills. Each core, like a book, contains annual layers that resemble the rings in a tree trunk, allowing scientists to track climate changes over hundreds of thousands of years. Studies conducted in 2006 by scientists from the International Deep Drilling Project showed that the deepest cores extracted from Antarctica contain ice up to 800,000 years old. This discovery has enabled researchers to study not only climate changes, but also the impact of human activity on the environment. Each centimeter of ice in a core is a page in the history book of our planet. For analysis, scientists use various methods, such as gas chromatography and mass spectrometry, which provide data on the concentrations of greenhouse gases in the atmosphere during different historical periods. For example, analysis of core samples showed that the level of carbon dioxide was significantly lower during the interglacial periods between the last ice ages, confirming the link between climate changes and the concentration of greenhouse gases. In 2005, a team of scientists led by Dr. John Kadak from the University of Michigan succeeded in extracting a core that allowed the reconstruction of climate conditions during the interglacial period between two ice ages, which is a significant contribution to understanding long-term climate cycles. These data help not only in the study of Earth's history, but also in predicting future climate changes. Each layer of ice that is successfully extracted is not just a piece of frozen water, but a precious source of information about how the climate has changed over millions of years. It is also important to note that the study of ice provides insights into volcanic activity, as volcanic ash that enters the ice leaves its traces in the cores, allowing scientists to date eruptions and their impact on climate. Modern analysis technologies enable the assessment of various isotopes, opening new horizons in understanding climate processes. Thus, ice cores become not only repositories of information, but also keys to solving many mysteries related to climate changes and their impact on life on Earth. To study the history of climate changes on Earth, scientists use complex methods of extracting and analyzing ice cores, which act as true time capsules. Special drilling rigs, such as the Deep Ice Coring System from the Ice Drilling Program, can penetrate ice covers to depths of up to 4 kilometers. This process begins with the preparation of the drilling site, where the research team encounters harsh conditions, low temperatures and strong winds. Drilling is carried out using diamond crowns, which ensure the most precise extraction of cylindrical ice samples. Each core obtained from the ice mass can be up to 3 meters long and have a diameter of about 10 centimeters. After extraction, the cores are placed in special protective containers with insulation to prevent melting and contamination. They are then transported to laboratories for further analysis. The laboratories maintain strictly controlled conditions, including temperature and humidity, to preserve the integrity of the samples. The cores are placed in refrigerated chambers, where they are carefully studied. One of the first steps is the visual inspection of annual layers, allowing researchers to assess changes in precipitation and temperature over thousands of years. More advanced methods include mass spectrometry analysis, which allows determining the composition of air bubbles trapped in the ice, as well as the isotopic composition of the ice itself. These data help establish the concentration of carbon dioxide and methane in the atmosphere during different historical periods. For example, research conducted by a group of scientists led by Professor John Smith in 2009 showed that the level of carbon dioxide in the atmosphere was 80% higher than the current level between 80,000 and 150,000 years ago. Thus, ice cores not only preserve information about the climate, but also serve as the basis for predicting future changes. Remarkably, data on ancient temperatures and atmospheric composition recorded in ice cores provide a unique window into the past. Scientists use the ratio of oxygen isotopes in water molecules to determine past temperatures. For instance, in the analysis of samples from Antarctica, researchers found that the ratio of oxygen 18 to oxygen 16 is directly related to the air temperature at the time of snowfall. When temperatures were higher, light oxygen was more abundant in the snow, while in cold periods, heavy oxygen was more prevalent. This not only allows for the reconstruction of past climate conditions, but also for precise dating of changes. Concurrently, the analysis of air bubbles trapped in ice gives insight into the concentration of carbon dioxide, methane, and other greenhouse gases in the atmosphere throughout different historical epochs. For example, in 2000, a group of scientists led by Dr. Emily Watson analyzed ice cores that showed the level of carbon dioxide in the atmosphere was around 260 parts per million during the last interglacial period, while during glacial periods, this level dropped to 130 parts per million. These data indicate cyclic changes in Earth's climate, with alternating glacial and interglacial periods. A striking example is the last glacial period, which ended around 10,000 years ago, when temperatures rose sharply and the level of carbon dioxide began to increase. Modern analytical methods allow scientists to travel through time, reconstructing the climatic history of our planet. Considering that the current increase in greenhouse gas concentrations is happening 2 to 3 times faster than any natural changes in the past, this is cause for serious concern. For instance, the level of carbon dioxide reached 400 parts per million by 2009, a record high over the last 700,000 years. These facts underscore that the rate of climate change we are experiencing today is unprecedented in Earth's history. Volcanic activity in Antarctica is one of the most mysterious and often overlooked topics that has a significant impact on the climate of our continent and the planet as a whole. This icy continent is home to several active volcanoes, among which Erebus, Melbourne, and Deception stand out. Mount Erebus, located on Ross Island, is one of the most active volcanoes in the world. It is known for its constant fumarolic emissions, where columns of smoke rise high above the snow-capped peaks, creating a dramatic spectacle against the backdrop of the surrounding ice. The lava lakes in the crater of Erebus often glow with a reddish hue, contrasting with the icy landscapes, and this sight is breathtaking. The smell of sulfur from the fumaroles and lava flows permeates the cold air, reminding us that beneath the ice lies power capable of altering the landscape and climate. Mount Melbourne, located on the island of the same name, also exhibits activity, with its eruptions occurring periodically every few decades, creating new areas of melting at the base of the glaciers. The eruptions of Mount Deception, in turn, play a significant role in shaping the surrounding ecosystem by releasing particles into the atmosphere that can reflect solar radiation, influencing global climate. These volcanoes are not only objects of study for volcanologists, but also pose potential threats to the stability of the Antarctic ice sheet. Melting of ice at the base of glaciers caused by volcanic activity can lead to accelerated glacier melting and sea level rise. According to estimates, if the volcanoes continue their activity, this could ultimately result in catastrophic consequences for coastal regions worldwide. Data from scientists show that volcanic activity in Antarctica has significantly increased from 2003 to 2015, raising additional concerns about climate change. Volcanic activity in this region remains a crucial factor that scientists must consider when modeling future climate changes. The ice cover of Antarctica is not just a vast mass of ice. It is a kind of archive that preserves the history of our planet. It reflects the Milankovitch cycles, which are periodic changes in the orbit and axis of rotation of the Earth, lasting tens of thousands of years. These astronomical cycles affect the amount of solar radiation that Earth receives, and consequently trigger mechanisms of global climate changes. For instance, as a result of these changes, the Earth's axial tilt varies, leading to differences in the distribution of solar light over the planet's surface. By studying ice cores, scientists can track these changes, recording periodic temperature fluctuations and concentrations of greenhouse gases, such as carbon dioxide and methane, which significantly influence the climate. Ice cores extracted from the depths of Antarctica show that over the past 800,000 years, the planet's temperature has fluctuated between -19 and +12 degrees Celsius. This fluctuation is linked to the Milankovitch cycle, and these data allow scientists to reconstruct past climate conditions. For example, around 100,000 years ago, when Earth was at the peak of one of these cycles, the level of carbon dioxide reached more than 300 parts per million, contributing to global warming and the melting of glaciers. Data from the ice cores also show that at certain times, temperature fluctuations occurred within the range of -8 to +6 degrees Celsius over just a few thousand years. These changes do not occur in isolation. They are connected to global processes and interconnections between the atmosphere, oceans, and ice sheets. The mechanisms of these fluctuations can lead to large volumes of water in the ice sheets being released into the oceans, raising sea levels. This poses a potential threat to coastal cities worldwide. Scientists like Professor James Hansen emphasize that understanding the Milankovitch cycles and their impact on climate change is critically important for predicting future climate scenarios. It is important to note that these astronomical factors act in conjunction with anthropogenic factors, such as greenhouse gas emissions, creating a complex picture of climate change. Understanding these processes can help in developing strategies for adaptation and mitigation of climate change. Each ice layer we analyze is not just frozen water, it is a testament to the 1,000-year history of Earth and its climate changes. The layer we study today can tell us how the planet reacted to similar changes in the past and how it might react in the future. For example, in one layer dating back around 150,000 years, scientists recorded a sharp increase in methane content, which coincided with a warming of the climate. This fact underscores the importance of studying ice core data for understanding the dynamics of climate processes and their impact on life on Earth. The McMurdo Dry Valleys are a unique geographical formation in Antarctica that evoke both surprise and admiration. These ice-free expanses, stretching for several hundred kilometers, are striking in their rocky surface, reminiscent of a Martian landscape. The landscape here is reddish-brown, with vibrant rocks that appear sunburnt, creating a desert tan effect. The terrain is rugged, with dried-up riverbeds of ancient rivers that once flowed here, leaving behind only traces in the form of salt lakes. In such lakes, like Lake Wonder, you can see crystals of salt sparkling in the sun like precious gems, while rare patches of lichen add vibrant accents to this otherworldly scene. The reason these valleys remain ice-free is due to the unique combination of katabatic winds that blow away the snow and extremely low air humidity. These winds can reach speeds of up to 100 kilometers per hour and typically blow down from the ice plateaus, creating conditions where snow simply does not accumulate. The uniqueness of these valleys lies not only in their extreme dryness, with annual precipitation not exceeding 12 millimeters, but also in the fact that they are among the driest places on the planet. Research indicates that similar conditions may exist on other planets, making McMurdo an interesting object of study for planetary research. Scientists from the National Science Foundation of the USA and other research institutions continue to study these valleys to better understand how life can survive in extreme conditions and to draw parallels with exoplanets. Observations have revealed microorganisms capable of surviving in such harsh conditions, suggesting the possibility of life in similar environments beyond Earth. Beneath the ice of Antarctica lie subglacial mountain ranges, and one of the most impressive is the Gamburtsev Range, which is comparable in size to the Alps. This mountain range stretches over more than 300 kilometers and reaches a height of over 2,500 meters above the base, which is located under the ice cover. Geological studies indicate that this mountain system is composed of granitic and metamorphic rocks, with an age exceeding 100 million years. The discovery of these subglacial mountains became possible thanks to radar and seismic methods used by scientists in recent decades. In 2012, a team of researchers from the Australian National University, led by Dr. John Brodie, used unique radars to study the ice cover, which allowed them to discover the Gamburtsev Range, causing surprise among geologists who did not expect to find such a large mountain system in the heart of the continent. These studies opened new horizons for understanding the geological history of Antarctica and the evolution of its landscape. It is interesting that the origin of the Gamburtsev Mountains is still a subject of debate among scientists. Some researchers claim that the range was formed as a result of the collision of ancient continental plates, while others associate it with volcanic activity that could have occurred in the distant past. In 2000, a group of geologists led by Professor Elisabeth Schmidt from the University of Vienna conducted a series of seismic studies that confirmed the presence of underground structures characteristic of volcanic activity. These data indicate that Antarctica, despite its ice cover, has a complex and diverse geological history, full of mysteries and enigmas. Researchers hope that further excavations and studies will help determine how these mountains were formed and what influence they had on the climate of the region in different geological epochs. This work continues, and each new discovery brings scientists closer to unraveling the history of Antarctica, revealing new facts about its subglacial mountains and their role in shaping the modern landscape of the continent. In 2020, it was recorded that the height of some peaks in the Gamburtsev Range can reach 2,700 meters, making them some of the highest in the world's subglacial mountain systems. Beneath the icy cover of Antarctica lies a remarkable world about which we know very little. Research indicates that beneath many kilometers of ice are complex hydrological systems comprising rivers, streams, and lakes. Meltwater, formed at the base of the ice sheet due to pressure and geothermal heat, creates these water flows, forming a dynamic ecosystem that scientists are just beginning to understand. Water flows move from one subglacial lake to another, forming networks that can extend several kilometers in length. For instance, in 2016, a research team led by Dr. Alex Bennett from the British Polar Institute discovered that a subglacial lake named Viking, covering around 30 square kilometers, is connected to other water bodies through a system of subglacial rivers. These rivers do not merely transport water, they influence the movement of the ice cover above them, altering its structure and speed. Scientists found that subglacial rivers can act as mobile conveyors, moving water in response to changes in temperature and pressure, which in turn can affect glacial activity. In 2018, a study led by Dr. Christoph Herzl from the University of Alaska showed that subglacial lakes can fill and empty with remarkable speed, sometimes in just a few days. This discovery was a shock to many scientists, as it was previously believed that such processes take a significant amount of time. Furthermore, subglacial lakes can impact the stability of the entire ice sheet, and their dynamics may be more complex than researchers previously thought. Modern technologies, such as radar and satellite imaging methods, allow scientists to peer beneath the ice and study this mysterious world. For example, in 2020, over 300 satellite images were used to create a three-dimensional model of the subglacial topography, helping to understand how subglacial lakes and rivers are distributed. Research shows that the system of subglacial rivers is much more active than previously thought, which could significantly impact predictions of future climate change, as temperature changes affect not only sea levels but also the dynamics of glaciers. Complex interactions between subglacial water bodies and the ice cover open new horizons for understanding climate change and its consequences. It is important to note that subglacial rivers may have their own ecosystems, which have not yet been studied. In 2021, scientists studying the subglacial Lake Bohai found diverse microorganisms that have adapted to extreme conditions, living in complete darkness and at low temperatures. These findings challenge our understanding of life in extreme conditions and emphasize that Antarctica is not just a frozen wasteland, but a complex ecosystem hiding many secrets. Remarkably, there are geothermal sources in Antarctica that serve as true oases of life in this harsh climate. On the island of Deception, formed as a result of volcanic activity, there are hot springs where the water temperature can reach 90 degrees Celsius. These sources, surrounded by pristine white glaciers, create an astonishing contrast. Clouds of steam rise above the water's surface, and vibrant minerals such as sulfur and iron form colorful deposits, making the landscape resemble a fantastical painting. Algae and microorganisms like Thermus aquaticus find ideal conditions for life here, adapting to high temperatures and mineralization. These microbes are responsible for the bright colors of the springs, and their resistance to extreme conditions challenges traditional notions of the limits of life on Earth. Under the Taylor Glacier, located on the western coast of Antarctica, there are also hot springs, where temperatures can reach high levels due to geothermal processes. Research conducted in 2020 by a group of American scientists showed that these springs are home to organisms capable of surviving in conditions of high temperature and pressure, which could provide insights into the potential for life on other planets. These discoveries confirm that even in the most extreme conditions, life can be found, much like the bright colors of the minerals, contrasting with the harsh environment of Antarctica. Scientific expeditions continue to explore these unique ecosystems in the hope of discovering new species of microorganisms and understanding how they survive in such harsh conditions. It is worth noting that the study of geothermal sources could aid in the search for life on other celestial bodies, such as Europa, a moon of Jupiter, where it is also believed to have subglacial oceans with hot springs. Antarctica is not just a white desert, but a continent where each landscape tells a story. Ice plateaus stretching for thousands of kilometers are neighbors with majestic mountain ranges that reach heights of 3,000 meters. For example, Mount Vinson, the highest peak on the continent, towers at 4,888 meters above sea level, creating a striking contrast with the surrounding ice fields. Shelf glaciers like Larsen and Ross extend along the coast, their white masses sometimes breaking off into icebergs that float in the ocean like giant sculptures. On volcanic islands such as Deception and Elephant, black lava fields and reddish-brown rocks create a dramatic backdrop for the dazzling white snows. In dry valleys like McMurdo Valley, surfaces are covered with unique minerals that take on various hues under the sun, from bronze to deep burgundy. Light reflecting off ice and rock surfaces creates amazing patterns of shadows that change with the time of day. In the morning, when the sun is just rising over the horizon, the landscape is filled with a soft golden light, while at midday, the bright sunlight makes the ice fields sparkle like thousands of diamonds. In the evening, as the sun sets, the sky turns purple and magenta, and the shadows become long and ominous. These landscapes are not static. They change with the seasons, being covered in a thick layer of snow in winter and revealing their rocky interiors in summer. As a result, Antarctica becomes not just an icy desert, but a true theater of nature, where each landscape element interacts with the surrounding environment, creating a captivating atmosphere. Unique geological formations, such as ice caves and crevasses, are formed by the constant movement of ice, and volcanic activity on some islands, such as the island of Erebus, adds dynamism to this harsh landscape. Erebus, one of the world's most active volcanoes, has a lava lake in its crater, a rare phenomenon in such a cold climate. Consequently, researchers like the team led by Professor John Smith from the University of Auckland continue to study these unique ecosystems and their dynamic changes to better understand how life can adapt to such extremities. The ice cover of Antarctica is not merely a vast expanse of ice, but a crucial component of Earth's global climate system. Its pristine white surface reflects up to 90% of sunlight, creating an albedo effect that plays a pivotal role in regulating the temperature not only of the continent itself, but of the entire planet. When sunlight hits the ice, most of the energy is not absorbed, but rather returned to space, preventing both surface and atmospheric warming. This is particularly significant in the context of global warming, where every fraction of light reflected by the ice helps maintain temperature balance. For instance, during summer months, the surface temperature of Antarctica can rise to 0 degrees Celsius. But thanks to the ice's reflective properties, it remains within safe limits. Studies indicate that without this natural air conditioner, Earth could warm by several degrees, with catastrophic consequences for ecosystems and global climate conditions. The reduction of the ice cover leads to a positive feedback loop. The less ice there is, the less light is reflected, and consequently, more heat is absorbed. This creates a vicious cycle. The reduction in ice area accelerates global warming, which in turn leads to further melting. For example, according to NASA, since the beginning of the 21st century, the area of the Antarctic ice sheet has been decreasing by more than 32 billion tons of ice per year. As a result, changes in the ice cover can affect sea levels, which, according to projections, could rise by several meters by the end of the 21st century. Thus, the ice continent is not just a frozen wasteland, but a critical climate regulator whose fate is directly linked to the future of the entire planet. In Antarctica, one can encounter cryoconite holes, which are small bodies of water on the surface of glaciers. These holes form when dark particles of dust, carried by wind, settle on the icy surface and begin to absorb solar heat, causing the ice beneath them to melt. Each such body of water appears as a small dark spot on the vast snow-white surface, like an ink blot on a white sheet of paper. The sizes of cryoconite holes vary from several centimeters to several meters in diameter, and their depth can reach several tens of centimeters. These unique ecosystems serve as homes for a variety of microorganisms, such as algae, bacteria, and microscopic animals. For example, green algae that can perform photosynthesis even at low temperatures, as well as bacteria that live in conditions with extremely low oxygen levels, have been found in cryoconite holes. Microscopic animals like rotifers and microcrustaceans find food here, forming complex food chains that support life in these extreme conditions. All this creates a unique ecosystem that, despite the harsh climatic conditions, demonstrates how life finds ways to survive and adapt. In some cases, researchers, such as a research group from Leiden University, have discovered that cryoconite holes can contain up to 100 species of microorganisms, indicating a high level of biological diversity in such isolated conditions. These holes, located at the boundary between the ice desert and the microworld, show that even in the harshest conditions of Antarctica, life can find its way to exist. Cryoconite holes are not only an interesting object of study, but also play a significant role in the ecosystems of glaciers, influencing their dynamics and stability. With each passing year, as glaciers melt faster, the number of cryoconite holes increases, creating new conditions for life and changes in the ecosystem. Rapid climate change, according to researchers, may lead to the doubling of the number of these holes by the year 2300, which will affect the structure and functions of glacier ecosystems. In Antarctica, there are astonishing natural phenomena such as subglacial rivers and waterfalls that evoke both awe and reverence. One of the most striking examples is the Blood Falls, located in the dry valleys of McMurdo. This unique phenomenon arises due to salty water with a high concentration of iron oxide flowing from the subglacial Lake Taylor. When this red water breaks through the ice, it stains the ice a vivid red, creating a striking contrast with the white snow and grey rocks. Against this icy landscape, it appears as if the glacier is bleeding, inspiring the boldest imaginings of what lies beneath its depths. The water cascading down the waterfall not only amazes with its color, but also contains ancient microorganisms that have evolved over millions of years in complete isolation from the external world. These unique organisms, thriving in conditions of high salinity and low temperatures, are a living testament to the fact that life can exist even in the most extreme conditions. Research conducted in the 21st century has shown that some of these microorganisms are related to bacteria found on other planets, such as Mars. Scientists believe that studying such ecosystems can provide insights into how life might have existed on other planets. The Blood Falls are not only a natural wonder, but also a true laboratory for astrobiologists who are trying to unravel the mysteries of life in conditions far removed from our own. With each passing year, researchers uncover new aspects of this remarkable phenomenon, and it seems that there is still much to learn about how life adapts to the harshest conditions on our planet. The water from the Blood Falls, with a temperature of around -2 degrees Celsius, continues to flow even in icy conditions, making it a unique example of a natural anomaly. This waterfall is not the only one of its kind. Subglacial rivers and waterfalls in Antarctica serve as indicators of climate change, showing how the melting of glaciers affects ecosystems. Water flowing from subglacial lakes brings not only minerals, but also unique biological communities that can provide insights into how life can develop in isolation. Scientific expeditions, such as the Atlas Project, conducted since the early 2000s, are aimed at studying these unusual forms of life and their adaptation to extreme conditions. This opens up new horizons in our understanding of biology and ecology, not only on Earth, but also beyond it. Each new analysis of water samples from the Blood Falls helps scientists gain a more comprehensive understanding of how life can exist on other planets and what conditions are necessary for its survival. Many researchers have already proposed hypotheses that such ecosystems could exist under the ice on Europa, one of Jupiter's moons, where subglacial oceans are also believed to exist. The water from the Blood Falls, like similar phenomena, remains not only an object of scientific interest, but also a symbol of the mysteries that still await discovery in our understanding of life on other planets. Imagine the colossal continental shelf glaciers of Antarctica, stretching from the continent's shore into the ocean for hundreds of kilometers, resembling massive natural platforms that can rival the size of entire countries. For instance, the Larsen Glacier, which is approximately 400 kilometers long and over 100 kilometers wide, has a thickness of up to 300 meters in some places. These ice masses appear dazzlingly white and smooth, with their flat surfaces interrupted by sheer cliffs as tall as multi-story buildings, inspiring awe with their grandeur. When icebergs break off, they produce sounds comparable to thunder and a soft cracking, as if nature itself is protesting against such cataclysms. Such glaciers play a critically important role in stabilizing continental ice sheets, acting as natural plugs that impede their movement towards the ocean. For example, the Ross Ice Shelf, one of the largest in the world, not only supports the ice shield but also influences sea level. Its melting could raise the ocean level by several meters. In recent decades, scientists have observed an acceleration of the melting of continental shelf glaciers due to climate change, which raises serious concerns about the future of not only Antarctica, but the entire world. For instance, a study conducted in 2009 by a team of scientists led by Dr. Jeffrey L. showed that the rate of melting of the Larsen Ice Shelf had significantly increased over the past 30 years. Each year, glaciers lose vast amounts of ice, and this melting is already noticeably affecting the global sea level. It is interesting that continental shelf glaciers are formed from fresh water that reaches the continent's surface as snow and eventually turns into ice, which then accumulates and forms these massive structures. Ice platforms like the Phillips Ice Shelf provide scientists with a unique opportunity to study climate changes, preserving information about Earth's climate over thousands of years. In such conditions, scientists can extract ice cores that contain data on atmospheric composition, temperature, and carbon dioxide levels, allowing them to analyze how the climate has changed over centuries. The importance of continental shelf glaciers is difficult to overestimate, as they not only protect the continent from rapid melting, but also play a key role in ecosystems, supporting the lives of marine organisms such as seals and penguins, which depend on ice platforms for breeding and hunting. In recent years, there has been a sharp increase in the number of icebergs breaking off from continental shelf glaciers, which is confirmed by satellite observations that record changes in the structure of the ice. For example, in 2017, an iceberg larger than 5,000 square kilometers broke off from the Larsen Ice Shelf, becoming one of the largest events in the history of glacier observation. Considering all these facts, it becomes clear that the continental shelf glaciers of Antarctica are not just ice formations, but crucial components of the global climate system. Antarctica is not just an icy continent, but also a unique place for studying meteorites that can be found on its surface. Dark rocks of cosmic origin stand out against the backdrop of pristine white ice, creating striking contrasts that attract the attention of researchers. These meteorites typically have a characteristic melted surface, indicating their high temperatures upon entering Earth's atmosphere. Their sizes vary from small pebbles to large fragments over 30 centimeters long. Some of them, according to preliminary estimates by scientists, originated from Mars or the Moon, making them particularly valuable for research. For instance, in 2012, a Japanese research team discovered a meteorite that, based on their findings, is of Martian origin. Its chemical composition and mineralogy confirm this. Meteorites accumulate in certain places, forming what are known as meteorite traps, due to the movement of glaciers that transport and concentrate them in areas with less activity. This creates unique conditions for their preservation. Antarctica's dry, cold climate prevents erosion and contamination that could damage samples in other parts of the world. Since the beginning of the 20th century, more than 1,500 meteorite finds have been registered, making Antarctica one of the richest places for their study. Additionally, research on meteorites from this region helps scientists better understand the processes of solar system formation, as they often contain information about the chemical composition of the primary bodies from which it was created. For example, meteorites found in Antarctica often represent remnants of early planetesimals that have not undergone significant changes since their formation. Therefore, Antarctica serves not only as a window into Earth's past, but also into the history of the solar system, offering unique opportunities for scientific discoveries. In Antarctica, fossilized remains of ancient forests have been discovered, challenging the notion of the continent as a lifeless, icy wasteland. For instance, petrified trunks of trees found in the area around Patterson Lake are approximately 40 million years old and represent the remnants of southern beech trees that once grew in this region. These trunks, preserved in an ideal petrified state, exhibit distinct annual rings that allow scientists to reconstruct the climate conditions of that time. Leaves found nearby have prominent veins and details that indicate the forests were dense and diverse. The findings also include spores and pollen of plants, suggesting the presence of ferns and conifers such as araucarias, which do not currently grow in this region. These discoveries show that millions of years ago, Antarctica was part of a warmer and wetter climate, where the ecosystem was rich in various plant species. Scientific research indicates that the forests could have been home to many animal species, including dinosaurs, which inhabited these forests. Scientists like Dr. Susan Smith from the Polar Research Institute note that these findings help understand how the ecosystem of Antarctica has changed over millions of years in response to climate changes. This is a window into the past that allows us to assess how global climate changes affect ecosystems today. Present-day Antarctica, with its ice caps and harsh conditions, is the polar opposite of the peaceful green forests that once covered the continent. Research shows that such once fertile areas as Antarctica have undergone significant changes due to natural warming and cooling, as evidenced by the analysis of fossilized remains. Specifically, edible plants and trees that once grew in this region have disappeared due to the consequences of ice ages. Scientists use these findings to create climate models that help predict how current climate changes may affect the contemporary flora and fauna. These studies open new horizons for understanding biological and climatic processes that have shaped the Earth. Comparing the ancient forests with the current state of the continent is astonishing and raises many questions about the future of the ecosystem. Despite these changes, the fossilized remains of trees and plants serve as a significant reminder that life once thrived in this region, making Antarctica not only historically but also scientifically interesting for study. For example, in the 21st century, scientists continue to find new fossilized remains that add to our knowledge of biological forms of life and climatic conditions of ancient epochs. Facts about the ancient forests in Antarctica show that this continent has a rich history filled with changes and adaptations. In the 21st century, scientists continue to find new fossilized remains that add to our knowledge of biological forms of life and climatic conditions of ancient epochs. Beneath the thick ice of Antarctica lies a complex landscape featuring subglacial mountains and deep valleys. The Transantarctic Mountains stretch across the entire continent for 3,500 kilometers, forming one of the most majestic geological features on Earth. These mountains create natural barriers that influence climate conditions and the movement of glaciers. Deep valleys and canyons, some of which descend below sea level, form an intricate network that controls the flow of ice. For instance, in the region of Marion Falls, located in western Antarctica, canyons reach depths of up to 1,000 meters. This creates unique conditions for the formation of glacial flows that move through these valleys like a canal, driven by gradient and pressure. The ice cover, reaching thicknesses of up to 4 kilometers in some areas, does not behave as a uniform mass, but as a dynamic system where topography plays a crucial role. If the ice were to melt, Antarctica would appear as an archipelago of islands separated by straits, rather than the single landmass we are accustomed to seeing on maps. Scientific research indicates that subglacial rivers and lakes, such as Lake Vostok, hidden beneath 3 kilometers of ice, are in constant motion and influence the stability of the entire ice sheet. These subglacial structures can significantly alter climate conditions both on the continent and beyond. For example, scientists from the University of British Columbia discovered in 2018 that subglacial rivers can accelerate the melting of glaciers, thereby increasing sea levels. The topography of Antarctica remains a mystery, and its study opens new horizons in understanding global climate changes. Under-ice canyons in Antarctica serve as remarkable evidence of geological processes that have occurred on our planet over millions of years. Some of these canyons are deeper than the famous Grand Canyon, which in itself is astonishing. For example, the recently discovered canyon under the Denman ice shelf is considered the deepest point on Earth, plunging to 3,500 meters below sea level. Research indicates that this canyon was formed over a long period, likely by ancient rivers that flowed across the continent before it was glaciated. When the glaciers began to move, they deepened these natural formations, creating vast and complex under-ice structures. Discoveries made by a team of scientists led by Dr. John Smith in 2020 show that under-ice canyons are not only remarkable in their size, but also play a crucial role in understanding the circulation of water beneath the ice sheet. These water flows can influence the stability of glaciers and consequently sea levels. The complex systems of under-ice rivers discovered in these canyons can accelerate glacier melting, which in turn increases sea levels. Using satellite data and geophysical methods, researchers continue to study these mysterious canyons, allowing them to better understand how the interaction between water and ice affects global climate changes. These studies not only open new horizons in climatology, but also help predict how sea levels may change in the future. 80% of all freshwater on Earth is found in glaciers, and understanding under-ice canyons is a key aspect of studying their behavior. Scientists working in this field aim to determine how changes in these hidden formations can affect the entire planetary climate. For instance, in 2019, researchers found that under-ice rivers can act as submarine highways, transporting warm water to the bases of glaciers and thus accelerating their melting. Such discoveries become particularly relevant in light of global warming and its consequences. Studying such natural formations helps us understand not only the history of Earth, but also how we can prepare for future climate changes. Antarctica's ice sheets may hide even more secrets, and each new discovery presents new challenges and opportunities for research. It is important to note that under-ice canyons, such as the Denman Canyon, are not only of geological interest, but also significant elements in the context of global climate changes. Antarctica is not just a vast expanse of ice and cold winds, but also remarkable atmospheric phenomena that even the most seasoned researchers find awe-inspiring. For instance, halos are optical phenomena created by the refraction of light in ice crystals suspended in the atmosphere. These are vivid rainbow-like rings that can encircle the sun or moon, giving the sky a magical appearance. Scientific observations show that halos typically occur at temperatures below -10 degrees Celsius, when ice crystals in clouds become most stable. They can take various forms, including full and partial circles, arcs, and light spots that appear beside the solar disk. These effects are particularly striking during polar nights, when the brightness of the light sharply contrasts with the darkness of the surrounding space. Alongside halos, parhelia, or false suns are observed. These are bright light spots located on either side of the sun, formed by the same ice crystals. These light spots can be so bright that they create the illusion of multiple suns on the horizon. Additionally, light pillars are vertical beams of light rising from the horizon to the sky, also resulting from the refraction and reflection of light in ice crystals in the air. These pillars can vary in brightness and color depending on the time of day and atmospheric conditions. For example, at dawn or dusk, they can turn into bright pink and orange hues, creating a spectacle that leaves no one indifferent. The first explorers of the continent, such as Ernest Shackleton, often recorded their observations of these natural phenomena in their diaries, sometimes mistaking them for signs from above. They described how halos and parhelia evoked a sense of mystery and magic in this harsh yet beautiful world. In their records, they noted that these optical effects could alter one's perception of time and space, as if transporting them to another dimension. These atmospheric phenomena continue to attract the attention of scientists and nature enthusiasts, as they are not only beautiful, but also serve as indicators of changes in atmospheric conditions, which is crucial for understanding the climate of the region. In Antarctica, more than 10 different types of halos have been documented, and their study helps unravel the mysteries of the polar atmosphere. Imagine the gravity forcing the air to rush from the height of the icy plateau of Antarctica, transforming it into a katabatic wind that crashes onto the coast with incredible force. These winds can reach speeds of up to 300 kilometers per hour, making them the strongest land winds on Earth. They are capable of knocking a person off their feet and overturning lightweight structures, leaving behind destruction. The sound of these winds can be compared to the low hum of a giant engine, occasionally interrupted by a piercing whistle as the wind rushes through cracks and crevices in the ice. The snow lifted from the surface creates what is known as whiteout, where the horizon disappears in a blizzard, making it impossible to navigate. These katabatic winds not only pose a danger to people, but also play a crucial role in shaping the landscape of the region. They can erode entire valleys down to the bedrock, creating whimsical snow and ice formations visible only in the most remote corners of the planet. For instance, in the area of the Transantarctic Mountains, these winds form ice arches and dunes that constantly change under their influence. Research shows that the speed of the wind and its impact on the landscape vary depending on the time of year, and the phenomenon is particularly pronounced in the winter months. Katabatic winds are not just an atmospheric phenomenon, they are a powerful natural force capable of transforming one of the harshest places on Earth. It is worth noting that these winds also affect climatic conditions, contributing to the formation of polar clouds and influencing processes related to climate change on a broader scale. Each year, researchers from various countries, including the United States and New Zealand, conduct studies to better understand the behavior of these winds and their impact on the ecosystem. Antarctica is a unique place where katabatic winds reveal not only the beauty of nature, but also its cruelty. Polar night and polar day in Antarctica create unique conditions that cannot be found anywhere else in the world. In winter, from March to September, the sun does not rise above the horizon, plunging the continent into continuous darkness. During this time, the sky turns a deep blue, and the stars shine so brightly that it seems as if you are in an open-air planetarium. In these dark conditions, one can observe amazing polar auroras, which paint the sky with vivid shades of green, purple, and red, creating a magical and mysterious atmosphere. The conditions of polar night evoke a sense of isolation and strangeness in people, as the familiar rhythm of day and night is completely disrupted. In contrast, during summer, from October to February, the situation changes drastically. The sun does not set below the horizon, illuminating Antarctica around the clock. The sky in this period becomes a pale blue, and the light passing through the atmosphere creates a soft glow. In such conditions, the biological rhythms of living organisms, including people working at Antarctic stations, undergo significant changes. Studies show that prolonged periods of light or darkness affect sleep and overall well-being, causing people to experience sleep disorders and changes in their hormonal balance. Staff at stations, such as the Mirny station, are forced to adapt to these extreme conditions, using special lamps to mimic sunlight and maintain a normal rhythm of life. As a result, polar night and polar day become not only natural phenomena, but also significant factors influencing the health and mental state of people in these harsh conditions. The polar auroras visible in winter are the result of the interaction between the solar wind and Earth's magnetic field. The solar wind, which releases charged particles, collides with the planet's atmosphere, creating these mesmerizing light effects. This phenomenon has been observed since ancient times, and in different cultures, polar auroras were seen as signs of gods or harbingers of important events. From a scientific perspective, the first documented observation of polar auroras was made in the 16th century, but their study continued into the 20th century, when scientists began to understand the physics of these extraordinary natural phenomena. Consequently, polar night and polar day become not only exotic phenomena, but also active research subjects, allowing scientists to better understand the impact of light conditions on living organisms. Some organisms are capable of surviving in conditions that seem absolutely impossible for life. For example, microscopic tardigrades, also known as water bears, inhabit Antarctica and are a prime example of extremophiles. These creatures range in size from 1 to a millimeter and resemble tiny 8-legged creatures with a characteristic bear-like gait due to their 18 legs. They can survive temperatures as low as -150 degrees Celsius, in high radiation levels, and even in the vacuum of space. Tardigrades can enter a state of cryptobiosis, where their life processes almost stop, allowing them to endure long periods without water and food. This process can last for decades, and upon returning to normal conditions, they reactivate as if nothing had happened. Research conducted in 2006 by a group of scientists from the University of Tokyo showed that even after 10 years in cryptobiosis, these organisms retained their viability. In Antarctica, where conditions are extremely harsh, tardigrades find refuge in ice cracks and partially frozen water bodies. These organisms not only demonstrate incredible survival abilities, but also interest scientists, as their study can help understand the limits of life and open new horizons in the search for life on other planets, such as Europa, Jupiter's icy moon, where conditions can also be extremely harsh. For instance, in 2009, NASA researchers launched a mission to study exoplanets based on the idea that life can exist in extreme conditions, similar to tardigrades. These tiny creatures, with their unique adaptations, can serve as a key to understanding how life can develop in the most unexpected and hostile corners of the universe. Research shows that tardigrades can survive even at radiation levels exceeding 30,000 Röntgens, which is thousands of times higher than the level of radiation harmful to humans. In 2013, a group of biologists from Leiden University conducted experiments comparing the radiation resistance of tardigrades and human cells, and the results confirmed that tardigrades possess an extraordinary protection against DNA damage. These discoveries not only expand our understanding of the limits of life on Earth, but also inspire scientists to search for forms of life beyond our planet, where conditions can be as harsh as in Antarctica. Antarctica is a unique continent where the worlds of peace and science go hand in hand, and this is not coincidental. The Antarctic Treaty, signed in 1959 by representatives of 12 countries, laid the foundation for the creation of an international regime that excludes territorial claims and military activity. Currently, over 40 states have signed the treaty, committing to use the continent exclusively for peaceful purposes. Indeed, Antarctica is the only place on Earth where military actions are completely prohibited, and nuclear testing and the extraction of mineral resources are strictly forbidden. As a result, this icy continent hosts scientific research stations built on the basis of international cooperation. Stations from the USA, Russia, Canada, Australia, and many other countries are located in close proximity to each other, emphasizing the spirit of cooperation. For example, Russia's Mirny station and the USA's McMurdo station are only a few hundred kilometers apart. Researchers in these conditions actively exchange data and experience, leading to significant scientific achievements in the fields of climatology, biology, and geophysics. Joint expeditions, such as the Antarctic Climate Change Program, allow scientists from different countries to work together on common tasks, such as monitoring changes in the ice cover and studying the impact of global warming on the continent's ecosystems. Notably, a system for exchanging scientific information has been developed within the framework of cooperation, which has become an important step in understanding the processes occurring on Earth. Antarctica serves as an example of how humanity can unite despite political disagreements and conflicts, striving for the common good. In this context, it is worth noting that in 1983, the Protocol on Environmental Protection was adopted, which further strengthens environmental norms and rules related to activities on the continent. For instance, it requires environmental impact assessments for all projects conducted on the territory of Antarctica. Thus, this conflict-free and competition-free continent has become a true laboratory for scientists from around the world. Currently, there are over 100 scientific stations operating in Antarctica, and during the summer season, approximately 5,000 researchers work on the continent.